So to begin with, for any structure to be able to stand up safely, whether it is a building or a bridge, it must have two stability systems. And these are, number one, gravity stability system. And the second one is the lateral stability system. So the gravity stability system, as the name implies, it is responsible to resist gravity loads, so i.e. vertical loads, such as the self-weight of the structure, any floor finishes, cladding weight, and also imposed load, so occupancy, people moving inside the structure itself. The other stability system is referred to as the lateral stability system, which is our main focus for today's webinar. And it is responsible to resist horizontal forces. Now, horizontal forces can arise either directly or indirectly. So example of direct horizontal loads are things such as wind loads and earthquake seismic loads. Indirect loads would be loads due to irregular shape of the structure. So maybe irregularity in plan or elevation, unbalanced loading. So higher loading on one side in comparison to the other side, eccentric loading. So as per the last bullet point, so in addition to providing your lateral stability system to be stable against horizontal loadings, it must also be ensured against eccentric loading. So eccentric loading is the case where you have your vertical loads acting at an eccentricity to the member. So it's not acting at concentric to the centroid of the member. Geometric imperfections. So as you know, there isn't any member, as far as I'm aware, that is perfectly straight. You will always have some kind of imperfections, whether these are fabrication imperfections, residual stresses, and these usually will also result in horizontal forces that you need to consider when you design your lateral stability system. Tolerances. So when you erect your building on site, you would always expect some, for example, out of verticality tolerances. These will also result in horizontal forces to be resisted by your lateral stability system. And lastly, asymmetric loading. So much more higher load on one side in comparison to the other. So moving to the next slide, this is a high-rise building called Capital Gate 1 Tower. It's located in Abu Dhabi. You can see the irregularity in elevation. The vertical irregularity in elevation will cause horizontal forces that the lateral stability system need to resist, in addition to, of course, the main horizontal forces coming from wind as well as other seismic forces. It is the main responsibility of the structural engineer to ensure that the lateral stability system that they choose is stable, robust, and safe. So if you imagine if you have a square or rectangular building on plan, you need to provide lateral stability system in both directions, so in the X and Y. And this is what I'm referring to in the first bullet point as in-plane and out-of-plane directions. So it is very important for the structural engineer to establish at a very early stage in the project, usually in the conceptual stage, what kind of lateral stability system they are going to go for, the magnitude of loads that the system is going to resist. So to help the structural engineer to decide on the type of the structural stability system to choose, there are many governing factors. Some of them are things such as the magnitude of the loads on the structure. So for example, if you're designing a high-rise building, you would expect your wind loads to be the dominant loads in your design. Your lateral stability system will be governed by wind loads. Geometry of the structure, as I illustrated in the previous slide. So do you have any irregularity in the shape in plan or elevation? Floor diaphragm type. So your floor, is it a rigid diaphragm, semi-rigid, or flexible? So example on rigid diaphragm could be things such as reinforced concrete slab, or if we're speaking about steel buildings, then you might have a composite metal deck with concrete on top. So basically, you need to make sure that your diaphragm is strong enough to transfer the force through the floor to the points where your vertical lateral stability system are located. Architecture requirements. Are there any big openings? So you can see on the right-hand side image, the frame highlighted in orange and green. So the orange part would be your gravity system, and basically whenever the load is applied on the roof, it gets distributed to the beam according to its tributary width, and then that goes as uniformly distributed loads that get resolved into reactions and then go as axial forces in your columns all the way down to the foundation to be resisted by the earth. The green arrow represent the lateral forces. So these will go into your bracing. In this case, we have an X bracing, tension and or compression, and then resolved into the other members all the way down to the foundation. So on the point of architecture requirement, you can see that the right-hand image, if there is a requirement for a big opening in that bay, that wouldn't be feasible because of the diagonal bracing and availability of materials. So of course, using local materials will always be cheaper than having to import other material on the overall project cost. So on this slide illustrates the main global instability failure mechanism that your structure need to be designed against. So you have overturning of your structure, racking sway, which we will focus on this webinar, sliding of your structure, and twisting, again, which is related to the lateral stability system, so the topic of this webinar. Basically, IS 800 2007, clause 4.1.2, classify your lateral stability systems into two main types. So you have braced, and sometimes referred to as non-sway type, and you have unbraced, again, sometimes referred to as sway type. So example of braced non-sway type would be steel bracings and in steel buildings, would also be reinforced concrete shear walls and or cores. Unbraced would be moment resisting frames. So you can see in the middle image that is an example of a sway moment resisting frame. In this frame, you have moment rigid connections between your beams and columns. Something to bear in mind when it comes to moment resisting frames or sway frames, as the name suggests, they are prone to second order effects. And the third type, which is basically a mixture of both. So you can mix match. You can have in one direction, you might have bracing and shear wall. In the other direction, you might have moment resisting frame. So you can have it either mix in a hybrid system in one axis or in both axes, as illustrated by the bottom image. Regardless of what lateral stability system you end up choosing, you must ensure that it has sufficient stiffness to restrict to an acceptable levels the sway deformations in any directions. So that basically means in both orthogonal direction, as well as twisting of the structure on plan, which will come to in one of the upcoming slides. So I mentioned earlier on that it is crucial for the structural engineer to have understanding of the load path in order to know the magnitude of the forces that the lateral stability system need to resist at an early stage. So the right-hand side image show you a wind load coming to act on the structure. So how this load will be transferred to the foundation. So the wind load will first hit the cladding of the structure as a wind pressure. And then depending on how the cladding panels are fixed to the structure, that pressure will be distributed to the beams and or columns, depending on their tributary width as uniformly distributed loads. These uniformly distributed loads will be resolved into end reactions that need to go into the floor diaphragm. And then depending on your floor diaphragm, again, which we spoke about earlier, so rigid, semi-rigid or flexible, it needs to transfer them to the location of your vertical lateral stability system. So as you can see on the right-hand side image, our main lateral stability system is a braced bay located on the right-hand side of the structure. So the floor diaphragm will deliver the forces to that bay. Forces will be resisted in the diagonals. In this case, the diagonals are in tension, and then the back columns are in tension, front columns are in compression, and then these will be delivered all the way down to the foundation and resisted by the earth. So looking at a shear wall, so these are the forces that your shear wall need to resist. So there will be a gravity component. So these are your vertical loads. And so you might have out of plane horizontal actions and in plane horizontal actions. Typically, you want your shear wall to be oriented in the long direction to resist the horizontal wind loads, because that's the major axis. This is the strong axis of the wall. And going on to the next slide, this is related to the bullet point that I mentioned before, that regardless of which lateral stability system you end up choosing, you need to make sure that it have sufficient resistance to torsional or twisting effects. So as you can see on the right-hand image, this is, let's assume that this is a plan of a floor of a building. And in here, we're relying on 3 shear walls to provide lateral stability. And you can see the stiffness centroid of the 3 shear walls are located just outside of the plan footprint. And the point of application of the horizontal load, which is the red arrow. So there is an eccentricity between the stiffness of the lateral stability system and your point of application of load. So that load times the eccentricity will result in torsional moment, twisting moment, that you need to account for when designing your lateral stability system. So this is what is stated in this bullet point. So torsional effects due to eccentricity between the centroid of the applied lateral load and lateral stability system centroid should be checked and kept to a minimum by properly distribute the location of the lateral stability system on plan, thus reducing twisting of the structure on plan. So this slide focuses specifically on braced, also known as this is about steel braced buildings. So using bracing for lateral stability. So steel bracings comes in multiple geometry. So you can either have single bracing, cross bracing, V bracing, knee bracing, eccentric bracing. So the IS 800 2007 clause 1.3.8 defined bracing consists of a diagonal members and are analogous to a vertical cantilevering truss. And it defined braced member as a member in which the relative transverse displacement is effectively prevented by bracing. So that means you have minimal inter-story drift at each story level. Steel structures that relies on bracing for their lateral stability usually have something referred to as simple construction. Basically, that means all the connections between the columns, beams, and diagonals are pinned connections. So that means there is no moment transfer at these joints. And pinned connections are usually cheaper to design, fabricate, and erect on site in comparison to moment connections, thus yielding in overall savings on the overall project cost. So I think I covered all of these bullet points. So going to the next slide, this is a building located in London, United Kingdom. And you can see it relies on an external bracing Diagrid to obtain its lateral stability system. So obviously this kind of lateral stability system need to be well coordinated with the architect, as it is visible and it have to look aesthetically pleasing. Going to the other type, which are sway frames, and an example of that are moment resisting frames. The main difference obviously here is that you have moment or rigid connections at the joint, so between your beams and columns. IS 800 2007, again clause 4.1.2, define them as connections are rigidly connected. For these frames, the assumption is that there is no relative rotation between connected members regardless of the applied moment. So how lateral stability is obtained then? It is obtained in these frames by the flexural behavior of the columns and beams. So this is what's providing the lateral stability of these frames. The problem with these frames is that they are susceptible to second order effects, and they are significant, and you need to take them into account by either using a moment amplification factor. So you take the forces that you obtained from your first order analysis, you magnify them, you design for these, or you need to carry out a full second order analysis, which I will come to in the upcoming slides. So this slide shows you a table highlighting advantages, disadvantages of each system in terms of horizontal drift, flexibility to opening, stiffness, ductility. So bracings, which are considered as non-sway frames. So this is relating to using steel bracing in steel buildings. So usually you obtain the lowest horizontal deflection with these frames, which is good. Therefore, they are stiff. Again, therefore, they are non-ductile, but the drawback is that they have low flexibility in terms of opening, as we've seen in one of my earlier slides. So if you have a cross bracing in one of the bays, and there's an architecture requirement to have a big opening, for example, for a delivery van to go through the building, that wouldn't be feasible. RC shear walls, cores, again, these are type of non-sway frames. Usually the lateral deflections are higher than what you obtain from the steel braced frames. They are more flexible to openings, as you can design your reinforcement and allocate for the opening where it needs to. They are stiff. They are generally ductile. So moment resisting frames, these are sway frames. Horizontal drift, usually you obtain the highest in these kind of frames in comparison to non-sway frames. They are very flexible to opening. That's a good thing, because you don't have crossing members that needs to cross the bay. So you have all the width and the height of the bay for any opening that you need to suit in. They have lower stiffness, and therefore they are more ductile with low natural frequency. Hybrid system, again, as the name implies, it's basically you mix and match between the different types to suit, to meet all the requirements that you have, whether architecture requirements, client requirements, and other involved parties. So let's assume that you have a high-rise building and it relies on a reinforced concrete core for its lateral stability, and there is a wind load acting on it. So that will be analogous to having a cantilever column, which is the red arrow represent the wind force acting on it, and then your structure will deflect the total deflection of delta, total horizontal deflection of delta. So that total deflection will be made up of two components. It will be made up of the flexural component as well as the shear component. So usually the higher, the taller your building is. So when you're dealing with high-rise building, the dominant component out of the total deflection will be coming from flexural deflection. The shorter your building is, then most likely it will be governed by shear deflection. A specific criteria for robustness, basically you need to ensure that your structure stay safe and serve its intended design life, and IS 800-2007 is no different. So some of these requirements: adequate resistance to horizontal forces should be provided for all structures, including portions between expansion joints. So basically what is this saying is, if you have a long structure on plan and you ended up having an expansion joint so that each portion of the structure will move independently of the other, then you must provide a separate lateral stability for each portion. You cannot rely on one stability system for the whole, for the two portions of your structure. Applied factored wind load at each level of the structure should not be taken less than 1% of that level's applied vertical dead loads. Reversal of loadings to be accommodated. So basically that means you need to consider horizontal forces from all directions. So if you're looking at wind or seismic, you need to consider all possible direction, not just one specific direction. Horizontal forces must be safely transmitted to the lateral stability system locations throughout the structure's cladding, floors, and roofs, by ensuring that they are securely attached to the main structure framework and have sufficient strength. So basically, these are things such as your cladding panels, glass panels need to be properly attached to the structural skeleton to make sure that the wind pressure acting on the cladding will be safely transmitted to the structural framework. And it includes things such as your diaphragm. So if you are assuming a rigid diaphragm, then you need to make sure that, for example, the metal deck is properly attached to the main structural framework with shear studs, so that the force will be effectively transferred to the locations of the vertical lateral stability system. And most importantly, even if you don't have any wind load, seismic load, and you think that you're fine and you don't have any horizontal force to consider, there's a minimum amount of horizontal force any structure need to be designed for, and it is referred to as the notional horizontal force. These account for things such as practical imperfections. So when you erect a structure on site, there might be some out of verticality tolerances, which might lead to eccentricity in the applied vertical loads to the centroid of members that will result in lateral forces that need to be resisted by your structure. And this is how we take them into account by using the notional horizontal force. And usually they need to be 0.5% of the total factored applied dead and imposed load on each floor. So you calculate the total factored and dead and imposed load on each floor. You multiply that by 0.5%, and then that point load needs to be distributed on each floor horizontally in both directions. Maybe you have more than 2 directions, but and these need to be combined with the gravity combinations only. You shouldn't combine them with the combination that already have lateral force in it. You don't apply them all in all directions simultaneously, so one direction at a time.